I'm Shi Qi from National University of Singapore. Today I'd like to talk to you about a new technique called Neuro-Symbolic execution. It is well known that symbolic execution has been widely applied in security for bug finding and many other tasks such as verification. And there exist many different tools which had surfaced over the recent 20 years. These tools target as symbolic execution for helping security applications. So what is symbolic execution? The main idea behind symbolic execution is that we're going to mark certain variables, such as x and y, as symbolic variables, and then reason about a set of values these variables can take in order to as the symbolic formulas, and these symbolic formulas will help us to reach specific states, such as the line 5 in this slide. And solving these symbolic formulas will help us to decide whether this path is feasible or not. One of the widely utilized variation of symbolic execution is called dynamic symbolic execution. In the remaining talk, I will refer it to DSE for short. Although symbolic execution is very powerful, it also has many limitations. Let's see these examples where there's a potential 0 divided by 0 box at line 30. To analyze this code, symbolic execution will meet 3 problems. The first problem is that it cannot solve the constraints generated at line 8 and line 9, which including the floating point variables, data, and value, due to the limited support for SMT solver. Second, it cannot reason about the function ABS due to the incomplete access to the code. Third, the analysis on the loop at line 11 and 12 will lead to path explosion. As you can see, each loop unrolling will generate 2 branches. Finally, in order to analyze this loop, it will generate 2 raised to 4k passes, which is intractable for dynamic symbolic execution. So in order to tackle these limitations, in our work, we propose a new approach called Neuro-Symbolic execution. It reasons about the exact and approximate constraints together. And given this approach, we also provide a tool called NeuEx, which enhances the widely used DSE engine called KLEE. And from our evaluation result, we show that our tool can find 94% more bugs than KLEE in 12 hours. So now, let's go back to the previous example that I just showed you. Given the source code of the program and the symbolic variables, such as the file name and the file in this example, which are specified by the users, and the candidate vulnerability points, which are generated by static analysis, the main goal of our work is to find the validated exploits for the program. So how can we find the validated exploit for the programs? As you can see, to analyze this piece of code, KLEE gets stuck. So what if we do not learn the exact representation? We do not analyze this code. We treat this as a black box. What if we learn approximated representation, which takes the values of symbolic variables as an input and outputs the values of vulnerable variables in CVP, instead of analyzing the exact representation of the source code? So why might this be helpful? This will be helpful if we can learn an approximation with a small number of observations, because sometimes it pays to not get lost in the details. So now, another question we will have is that, can we indeed learn an approximation with a small number of observations? If we can do that, then it can release the burdens of analyzing this code. And in fact, I want to show you that for these particular examples, we can indeed learn several simple facts that approximate this complicated program logic. As you can see, for this specific loop, which will lead to path explosion, actually, we just need to learn the count of empty elements inside the variable file. Similarly, we have another simple fact that can approximate the logic of unknown function FABS and floating point variables. So the approximation that we need may not need to be very accurate. Once it can learn the correlationship between variables, it is enough for our analysis. And this kind of approximation actually can be learned by using machine learning techniques. So specifically, what kind of approach that we can use to learn this approximation? Here, in this work, in order to make it more general, we decided to use neural network to learn the approximate constraints. So there are two reasons for us to select neural network as the main technique. First is that neural nets can represent a large category of approximations of functions as shown in universal approximation theory. Second, in practice, multiple applications have shown that neural nets are learnable for many practical functions. So now, given the insight that we built an end-to-end tool called NeuEx on top of KLEE, which is one of a widely used symbolic DSE engine. We feed this input into NeuEx and use these three as the backend SMT solvers. NeuEx will keep executing in DSE mode until it finds bottlenecks, which includes unmodeled APIs, loop unrolling for more than 10K times, D3 timeout, and memory exhaustion. Every time when NeuEx, when DSE mode meets a bottleneck, it will trigger a neural mode here. This neural mode is going to handle the remaining complicated logic, and the DSE mode will go back to the analysis for the other passes. Finally, we will going to generate the validated exploits for the programs. So given the bottleneck that encountered by DSE and the candidate vulnerability points, neural mode will first randomly mutate the concrete states generated by, collected by DSE and concretely execute the programs to check which CVP is feasible from the bottlenecks. Then it will continue this random mutation process to generate as many IO examples as possible. However, not all the CVPs will have sufficient samples. Thus, we will only select the one with sufficient samples for our training. After we train the neural network, we will solve the trained neural network with the symbolic constraints generated by DSE together. So now, let's go back to the previous examples that we have. So what kind of constraints that we will generate finally? As you can see in these examples, we will generate two kinds of constraints. The first one is the reachability constraints, which include one symbolic constraint generated by the DSE mode at line 2, and one neural constraint used to approximate the complicated logic from line 8 to 12. And then we will also have the vulnerability condition, which tell us when this vulnerability will be triggered. These two constraints can be classified into two classes. One, the pure constraints. As you can see in this example, we will have these purely symbolic constraints, which do not share any variable with the neural constraints. These constraints can be simply solved by SMT solvers. The other constraints that we will get is called mixed constraints, which include both neural constraints and symbolic constraints with shared variables. Since these constraints, including neural constraints, it cannot be directly solved by SMT solvers. Thus, how can we solve these constraints? So to solve these constraints, we actually have multiple choices. The first choice is that we can encode our neural network into a CNF formulas and solve these CNF formulas with symbolic constraints together. The second choice is that we can actually transfer these symbolic constraints into a differentiable functions and then use this function as the optimization objective of the neural nets. Both approach is possible. However, for the first approach, the number of clauses increases drastically with the increase in the complexity of neural nets. Thus, only the second choice is possible in practice. So how can we encode symbolic constraint as the objective, as the optimization objective of neural nets? Let's look at these mixed constraints that we have before. Here we have one symbolic constraint, value plus count minus 3 is equal to 0. In order to generate a proper optimization objective, we need to satisfy the one criteria, which is that the minimum point of this loss function that we generated have to satisfy the symbolic constraints, which means for these cases, the minimum point of the loss function should be that where value plus count is equal to 3. One possible encoding for this one is that the loss function is equal to the absolute value of value plus count minus 3. We also have the encoding scheme for other constraints. More details can be referred to the papers. So now we already have these encoded symbolic constraints with the neural constraints. How can we solve it? To solve it, we can directly use standard optimization approaches, such as gradient descent. What we do is that we calculate the gradients regarding to the input variables phi, and we keep updating the input variable phi until one times the loss reach the minimum point. At that time, we will generate one possible input, and then we will concretely execute our program with this input to validate whether this is indeed exploit or not. Now, let's look how our NeuEx works. Recall that neural mode is only triggered when DSE encounter bottlenecks. That means if DSE does not encounter any bottleneck, our NeuEx will work exactly as DSE mode. So to evaluate the performance of our NeuEx on handling these limitations of DSE, we evaluate our approaches on 7 programs which are known to be difficult for classic DSE. These programs include complex loops, floating point variables, and unmodeled APIs. First, we measure the performance of classic DSE mode by counting the number of CVPs covered by them. And from this graph, we can see that the number of CVPs covered by DSE increased dramatically, but later on, it gets stuck. The reason why it gets stuck, mainly because of it met the bottlenecks that we mentioned before. And during our analysis, we found that most of the bottlenecks actually are complicated loops. Some of them are unmodeled APIs, and the remaining ones are due to the Z3 timeout and the memory exhaustions. However, on the same conditions, we also do a similar evaluation of our NeuEx. As you can see, the number of CVPs covered by NeuEx keep increasing. And for our result, we find that the number of CVPs covered or reached by our NeuEx is actually 25% higher than the vanilla KLEE in total. Apart from the CVP coverage, we also measure how many bugs found by NeuEx and KLEE. And we found that NeuEx finds 94% and 89% more bugs than vanilla KLEE in both BFS and random mode in 12 hours. Apart from the comparison to KLEE, we also do the comparison to the other extension to DSE, which try to solve the limitation of the classic DSE. Here we compare to LESE and vary testing. LESE is a structured approach for loop reasoning, which try to solve the constraints use SMT solvers. And during our experiments on the same benchmark, we found that LESE is actually 2 orders of magnitude slower on average compared with NeuEx. Similar evaluation has already been done on vary testing, and which combines both the dynamic symbolic execution with static analysis together. And in our experiments, we found that vary testing fails to find bugs that we tested in 12 hours, mainly due to the poor instruction coverage. So in conclusion, the key takeaways of our work is that we propose a new approach called Neuro-Symbolic execution, which resolves the fundamental limitation of classic DSE. And this is the first work to learn the unstructured representation, which is not amenable to SMT solvers. Also, this is a unique use of optimization technique and SMT solver together for solving the constraints. And for our evaluation result, we show that our tools indeed can find 94% more bugs than KLEE within 12 hours. That's all for my talk. I'm happy to take questions.
while the others are coming to the mic, I actually have a question about this work. So this is a really, really interesting idea, and I think it may open up a lot of opportunities to make symbolic execution more practical. My question is that with the Neuro-Symbolic execution, what you're doing is seems like you're approximating the tricky functions, and I'm wondering how accurate and precise the neural networks can be at evaluating what those what it's actually approximating.
Oh, this is a very good question. Actually, for our experiments, for most of the cases, our neural network can learn a precise approximation for the models. But there indeed exist cases that our model cannot learn. Among our experiments, actually we learned 29 models in total, but only 20 exploits were generated finally.
Okay, thank you.
Heng Ying from UC Riverside. Great work. So in your evaluation, you showed that there are a few cases KLEE got stuck is because some API is not modeled, and there are many other more cases because the complex loops.
Yes.
So I wonder, for your improvement, I understand that your improvement can somehow, generate a model for these APIs. Can you explain or talk about whether your approach can solve complex loops?
So the thing is that maybe I can go back to the previous slide.
Right.
So here, for example, in these cases, these loops will lead to a path explosion, right? And actually, our neural network is able to learn this simple fact that this loop is just counting the number of elements within the number of empty elements within this variable file.
Oh, okay. All right. Gotcha. Thank you.
Hi, Director Severino Eastern. Very, very interesting talk. I wonder if you could talk a little bit more about how you identify the candidate vulnerability points.
Oh, this we identify it mainly by static analysis using existing tool. So there's nothing new for identify in the candidates.
Okay, thank you.
Xiang Kunjia from Penn State. So it is a quite quick question. For this example, how do you decide how much code do you choose for a sample for the training? How many lines of code? So you want to use the machine learning to learn the data relationship between of some code snipes.
Yes.
So how many code in the snipes?
Oh, you are talking about which part is modeled by neural network,
yeah,
right?
Do you know it is a function level or?
So the thing, it may not be a function level. So the input for the we modify the code snips start from the bottlenecks to the CVPs.
Okay, got that. Thank you.
Hi, this is Nikos from the University of Florida. Very nice talk. A very quick question. I understand that your control variable in the optimization problem is discrete time, right?
What? Sorry?
The control variable in your optimization problem is discrete time, not continuous time, right?
Sorry?
Like you have an optimization problem, right? And you try to optimize a value, right? Can you go to the optimization problem?
Oh, yeah. You're talking about this one?
Uh,
Next slide.
Like you try to optimize, like what's the control variable that you try to optimize? Like it's the number of, it's what exactly is the variable that you try to optimize?
Oh, I see. So the variables that I'm trying to optimize is the shared variables between neural constraints and the symbolic constraints.
And are they discrete time or continuous time?
It can be discrete time or continuous time. So if it's discrete, then when we do when we try to generate exploits, we will ask it to update one by one. If it's continuously, we will update it according to the gradient.
But if it's discrete time, then the gradient descent is valid, makes sense. Your solution, the gradient descent, makes sense also for the case that is discrete time. I'm just wondering. Okay, sounds good. Okay, thank you.
Thank you.